Hello everyone, welcome to Vyas Edification. In this session we are going to discuss chapter number 9 of class 11th mechanical properties of solids. Clear? So, in this session you will find detailed solution of each and every question of NCERT and questions, as well as you will find the theory behind that question also. Clear? So, by the way of question, we can say through the questions you will get some concept that is related to this chapter. Clear? So now we are going to discuss all questions, so concentrate on a screen. So dear student, we are going to discuss question number 9.1, and in this question it is given to you, we have a steel wire of length 4.7 meter and cross-sectional area 3 into 10 to the power minus 5 meter square stretches by same amount as a copper wire of length 3.5 meter and cross-sectional area is given to you 4 into 10 to the power minus 5 meter square. Clear? Now, it is also given under a given load. Clear? So, what is ratio of Young's modulus of steel to copper? Clear? So, dear student, actually how can we define Young's modulus? That is very important. So, we can say within our elastic limit, or we can say within a proportionality limit, stress is directly proportional to strain. Clear? So whenever we write stress is equal to something constant into strain, so that constant is actually, we can say, modulus of elasticity. Clear? So this modulus of elasticity is also actually we can divide in three types. Clear? Young's modulus, shear modulus, and we can say modulus of rigidity. Clear? So in this question it is given to you. Yes. So if we talk about this question, in this question it is given we have a steel wire. So let's suppose I am saying this is steel wire. Clear? Let's suppose this is a steel wire. Clear? Length of this steel wire is given to you 4.7 meter. Clear? So directly I am writing here. Yes. So length of steel wire. So length of steel wire, this is 4.7 meter. Clear? And cross sectional area of this steel wire, it is given to you 3 into 10 to the power minus 5 meter square. This is given in a question. Clear? It is stretched by same amount. Clear? So let's suppose I am saying here deformation delta x1, this is equal to delta x, for example. Clear? So stretched by same amount as a copper wire. So now we are talking about copper wire. So for copper wire, length of copper wire given 3.5 meter. So we can say this is equal to 3.5 meter. Clear? Okay. And cross sectional area. So cross sectional area of copper wire, this is provided to you 4 into 10 to the power minus 5 meter square. Clear? Under a given load, it means we can say external load, or we can say normal load that is acting on this steel wire is same as the copper wire. Clear? So one more thing is given to you. It is stretched by same amount. It means I can say, let's suppose deformation in copper wire we have same as deformation in steel wire. Clear? Now our objective here is to calculate value of Young's modulus. Clear? So Young's modulus is actually defined as, we can say, stress over strain. Clear? Young's modulus is defined as stress over strain. Clear? So I can say Young's modulus stress. Stress is defined as force per unit area. Clear? And it is divided by, I can say this is delta x by L. Clear? So now I can say y, this should be equal to FL over A delta x. Clear to you? So if I talk about, this is a formula related to Young's modulus. Clear? Now our objective in this question is to calculate ratio of Young's modulus of a steel wire. So I can say this is Young's modulus of steel wire and over Young's modulus of copper wire. Clear? So for steel wire we can say, if I write here F, this is LS over AS and this is delta x. Clear? This is for steel wire. We can also write same for copper wire. So this is L copper wire. We can say area copper wire and this is delta x. Clear? So from here we can say this delta x and delta x cancelled out. This F is cancelled out. Clear? So I can say LS over L copper multiply LX over L copper multiply, I can say A copper over, I can say A steel. Clear everyone? So now we can say, we can write like this, Ys over Y copper, this is given by length of a steel wire. we have 4.7 meter, clear, divided by length of copper wire. So length of copper wire we have 3.5 meter, multiply area of copper wire. Area is given to you 4 into 10 to the power minus 5, clear, divided by, now area of a steel wire 3 into 10 to the power minus 5, clear. So I can say this one and this one cancelled out, clear. So from here can we find here value of Ys over y, Ys over y copper? Yes, directly you can see. We can say this is 3 multiply 3.5, clear. So we can say 15, listen carefully, 15, clear. We have 1, so this is 10.5, clear, and in numerator we have 4.7 multiply 4, so we can say this is 8, we have 2, this is 18.8, clear. So now if we divide this 18.8 with 10.5, so approximately you will find this value equal to 1.76, clear. So now we can say Young's modulus of this steel wire is 1.6 times of Young's modulus of copper wire, clear to you. So this is a ratio of Young's modulus of steel and copper, clear. So this is all about this question. Now student, we are going to discuss question number 9.2, and in this question it is given to you a figure shows stress and strain curve for a given material, okay. What are number 1 Young's modulus and second approximately yield strength for the given material, clear. So first of all I am going to solve here part number A. So whenever stress and strain is strain and stress curve is given to you, clear, and if we are talking about this graph within proportionality limit, clear, so we can say within proportionality limit stress is directly proportional to strain, and directly we can say Young's modulus. So how can we find this Young's modulus? So we can say from here to here, definitely we can say here we have a straight line. So if you find slope of this graph, it will definitely provided you Young's modulus, yes or no. So we can say actually Young's modulus value, it is equal to what? Slope of stress strain curve, clear. I can say slope of stress and strain curve, this is given by Young's modulus, clear, this is given by Young's modulus. So how can we write here value of Young's modulus? Simply I can say we can say here you can say we have a coordinate, so coordinate is 0.002150, clear, and I can say here we have coordinate 0, 0, clear. So how can we find here slope? That is y2 minus y1 upon x2 minus x1, y2 minus y1 over I can say x2 minus x1, clear. So y2 minus y1 upon x2 minus x1, so y2 equal to what? This is 150 minus I can say y1, this one equal to 0, clear. x2 is given to you 0.002 minus I can say this is 0, clear. From here we can say this y is given by 150 divided by 0.02, or we can say this is equal to 150 divided by 2 multiply 100, and this is in Newton per meter square, clear. So now I can say Young's modulus is given by 75 into 100, clear to everyone. This is what we can say 150 divided by 2, and we can say this one, clear. But always keep in mind this value we have multiplication of 10 to the power 6, clear. So don't forget it. So we can write this is multiplied with 10 to the power 6. Here we also have 10 to the power 6, clear. So we can write like this, clear. So from here we can say we have Young's modulus value 7.5 into 10 to the power 9 Newton per meter square, clear. So this is a value of Young's modulus, and this is the answer of part number A, clear to everyone? Yes. Now we have to calculate here approximately yield strength for given material, clear. Yield strength means what? We can say maximum stress that is generated in a wire, given wire, that is known as maximum yield strength. And actually we can say yield, this point is actually defined as a yield point, because after which actually this graph is given for you a brittle material, clear. As the yield point reaches this material actually fractured, clear. So we can see directly this value this value is approximately equal to 300 multiplied 10 to the power 6 Newton per meter square stress. Clear? So we can say this is a value of yield strength. Clear? So if I talk about part number B, I can say yield strength. I can say yield strength, and this yield strength is given by 300 into 10 to the power 6 Newton per meter square. Clear to everyone? So yield strength is given by 300 multiplied 10 to the power 6. Clear? So this is all about this question. Clear? Now we are going to discuss question number 9.3, and in this question it is given to you the stress strain graph for material A and B are shown in figure. Okay, fine. The graph are drawn to same scale. Fine. Which of the material has greater Young's modulus? Clear? So actually if you observe here two graphs, graph number A and graph number B, clear, approximately we can say this graph is actually not a perfect clear to you. Actually here it should be provided that what is this angle. Clear? But I am saying to you this angle, let's suppose I am saying this is theta 1 and this is theta 2. Clear? So I am saying here theta 1 is greater than theta 2. Clear? So definitely we can say slope of graph A is more compared to slope of graph B within proportionality limit. Clear? Okay, what is proportionality limit? So proportionality limit is the point up to which stress and strain is linearly vary. Clear? Or we can say stress is directly proportional to strain. Clear? So directly we can say theta 1 is greater than theta 2. So definitely we can say slope of A is more. Slope of A is more compared to slope of A is more compared to slope of B. Clear? Slope of A is more compared to slope of B. Clear to you? Now we have part number B. Which of the two is a stronger material? Clear? So if we are talking about stronger material, actually this graph should be like this, somewhat like this, like this. Clear? So now we can say if we are talking about stronger material, clear, stronger material means directly we can say in this point you are getting that this ultimately tensile strength. Clear? Actually we can say this is a graph. Clear? And if we are getting like this, it means we can say here ultimate tensile strength of the given material is more. Clear? It means definitely we can say before fracturing this material A, this is more stronger. Clear? So I can say material A is more stronger. Material A is more stronger. Material A is more stronger compared to B. Material A is more stronger compared to B. Clear to everyone? Clear? Yes. Clear? So this is all about this question. Clear? Now dear student, we are going to discuss question number 9.4, and in this question it is given to you, read the following two statements below carefully and state its reason it is true or false. So now question is related to true or false. Now listen carefully. First of all, in part number A, it is given to you Young's modulus of a rubber is greater than that of steel. This statement is we have false. Clear? Why this is false? Actually, let's suppose if we are talking about this is a road. Clear? And let's suppose first this road is made up of steel, and second one let's suppose this is made up of rubber. Clear? Now let's suppose I am applying here loading condition. Let's suppose this is tensile force, that is F. Clear? And let's suppose I am saying this is cross sectional area A. Clear? So now I can say if I write here delta x we can write like this FL over AY. Clear? Now listen carefully. Loading condition is same for both wires. Length of this wire I am also taking, that is same. Clear? If we are talking about cross section area is same. Clear? So directly we can say this deformation is inversely proportional to Young's modulus. Clear? Clear? So you can also write like this, Young's modulus is inversely proportional to delta x. Clear? So if we are applying same loading condition, definitely you know by common experience that rubber will elongate it more compared to steel. Clear? So it means we can say when delta x is more, definitely we can say y will be less. Clear? So I can say Young's modulus for steel wire is more compared to, I can say this is rubber. Clear? So now we can say actually there is a different meaning of elasticity in our physics. Clear? In general, in our everyday life, we see a body that elongated more, it is having more elasticity. But in physics, we can see that in a same loading condition, if a body elongated less, it is more elastic. Because in physics we define elasticity like this, that it is the capability of a body to regain its original size. Clear? As soon as possible. Clear? So we can say here we are talking about Young's modulus. Young's modulus of steel is more compared to rubber. So we can say steel is more elastic compared to rubber. Clear? So I can say this statement we have false. Clear? Now if I am talking about part number B, the stretching of a coil is determined by shear modulus. Now listen carefully. Let's suppose here we have a coil. Clear? Let's suppose I am exerting a force in this direction like this. Now you can observe, as we are applying here tensile force, due to this tensile force this spring is elongating. Yes or no? Due to this force this spring is elongating. So when this spring is elongating, it means I can say the length of that coil as well as area of that cross section area of that wire, that is not changing. Clear? It means we can say due to this force only shape of this coil is changing. Clear? So definitely we can say stretching of a coil, it is determined by shear modulus. Clear? So I can say this statement is true. Clear? So this is all about this question. Now student, we are going to discuss question number 9.5, and in this question it is given to you two wires of diameter 0.25 centimeter made of steel and other made of brass are loaded as shown in a figure. Fine. The unloaded length of steel wire is 1.5 meter and for brass this is 1 meter. Clear? Now what is my objective? My objective is very clear. We have to find elongation of steel and brass wire. Clear? So now concentrate on a screen. So if I am talking about elongation part, clear? So we know very well, formula for elongation, this is given by FL over AY. Clear? So now we can say if I am talking about steel, if I am talking about steel wire. Clear? So if I am talking about steel wire, I can say elongation in steel wire, that is given by F, I can say LS divided by AS, and I can say this is YS. Clear? Now important part is here, whenever I am talking about steel wire, so what is external loading that is taking place here? So I can say here we have 4 kg, I am neglecting mass of this wire, that is brass wire, and we can say this is 6 kg. So total if we talk about 4 plus 6, total 10 kg weight is hanging on this wire. Clear to you? So I can say we can write like this, this is 10 and we can multiply it with G. Okay, length of steel wire. Length of steel wire is given to you 1.5 and divided by, if we are talking about area, cross section area of this steel wire, so it is given in the question, yes, diameter is given to you, so we can write like this, pi r, we can say 1.25 into 10 to the power minus 2 whole square. Clear to you? And what about Young's modulus? Young's modulus of a steel wire, we have 2 into 10 to the power 11 Newton per meter square. Clear? So from here we can write like this, delta xx, this is given by 100 into 1.5 divided by 3.14 into, I can say this 0.125, this is equal to 1 by 8, so 1 by 8 multiply 1 by 8 multiply 10 to the power minus 4, and this is 2 into 10 to the power 11. Clear to everyone? So now we can see this one we have a 4. Clear? So I can say this is 150 divided by 3.14. Clear? Multiply with 8 multiply 4, and this is 10 to the power 7. Clear? So now I can say approximately if I am taking this is 3. Clear? So definitely we can say here we will find this is equal to 50. Clear? Approximate calculation I am taking. So approximately 50 into, I can say 32 into 10 to the power 7. Clear? So now if you multiply, you will find here this is 0, we have 1, so 160. Clear? So 160 into 10 to the power 8, and I can say this is meter. Clear to you? Yes or no? Okay. One more thing is here. Here you will find minus 7. Clear? So this one is minus, this one is also minus. Clear? So from here we can see elongation, this is produced in a steel wire, that is given by approximately 16 into 10 to the power minus 7 meter. Clear to everyone? Or definitely the elongation will come slightly less because this is 3.14. Clear? That's why we are actually assuming here value, we are assuming value of pi that this is equal to 3. Clear? So we are getting here 160 into 10 to the power minus 8. Clear? So this is all about wire steel. Clear? Now same if we calculate for brass wire. Listen carefully. Same if I calculate for brass wire. So for brass wire I can actually put here all values like this. If I am talking about this brass wire, the total amount of mass this is hanging, we have 6 kg. Clear? So I just write here, instead of 10 I will write only 6. Clear everyone? So I will write here this is 6. Clear? 6G, we have length of a brass wire that is equal to, we can say 1.0. Clear? So here we have 1.0. Now radius of brass wire is also same. Clear? And now if we are talking about Young's modulus value. Clear? So Young's modulus value for copper wire. I am writing here Young's modulus value for copper wire. Clear? So what is value of Young's modulus for copper wire? Again, do not memorize it. I am just telling you that value is given 0.91. 0.91 into 10 to the power 11 Newton per meter square. Clear? This will be definitely given you in a question. Clear? Now if we solve, definitely after solving it we can find our answer. Clear? So now concentrate on a screen. Yes. Now concentrate. Now we can solve it. Let's suppose we can say this is 60 multiply 1 divided by, I can say this is 3.14 multiply, this one is what, 1 by 8. So I can say 1 by 8 multiply 1 by 8 into, I can say 10 to the power minus 4 into 0.91 into 10 to the power 11. Clear to you? So now we can say 60 into 8 divided by 60, we can say 60 multiply 8 divided by 3.14 into 0.91 into 10 to the power, I can say 7. Clear? So now we have to solve it and definitely we can get our answer. Clear? So now listen carefully. Yes, here we are talking about deformation that is produced in a copper wire. I can say here we have a copper wire. Clear? At all place we will write here copper. Clear? So we can say here we have a copper, this one is also for copper and copper. Clear? So, actually sorry, this is a brass. I am extremely sorry, this is for brass. Clear? So we can say here we have brass. Clear? Here we have brass, this one is also for brass, this is one also for brass. Clear? So Young's modulus for brass, this is given to you 0.91 into 10 to the power 11. Clear? Now we are solving it. So we can write like this, delta x. Delta x is given by 60 into 8 into 8. 60 into 8 into 8 divided by, now we can say 3.14 and this is 0.91. So if you say approximately, I am taking this multiplication approximately equal to 3. Clear? So this is 3 into 10 to the power 7. So we can write like this, this is approximately 20 into 8 into 8 into 10 to the power minus 7. Clear? So from here I can write value of delta x in a, or we can say deformation in a brass wire. This one is given by 64. Clear? 64 multiplied to 128. So 128 0 into 10 to the power minus 7. Clear? So from here we can say, we can write like this. This is 10 to the power minus 7. So 1.28 into we can say 10 to the power minus 5. Clear? So dear student, actually we can say this is 10 to the power minus 4. Clear? I can say this is 10 to the power minus 4 and we can say this is a value for deformation, this is produced in a brass wire. Clear? So this is all about this question. Now dear student, we are going to discuss question number 9.6, and in this question it is given to you the edge of an aluminium cube is 10 centimeter long. Clear? Okay. One face of a cube is firmly fixed to a vertical wall. A mass of 100 kg is then attached to opposite face of a cube. The shear modulus of a aluminium is given 25 gigapascal. Now, what is vertical deflection of this face. Clear? So now concentrate on a screen. Let's suppose if I am drawing here, this is a cube. Let's suppose I am saying this is a cube. Clear? And let's suppose we fixed this particular, we can say we fixed this as a wall. Actually we fixed this face for to the wall. Clear? So this face is fixed. Clear? It is given in a question. The edge of an aluminum cube is 10 cm long. So we can say, because this is a cube and side of this cube is also given 10 cm. Fine. One face is fixed and other on other face we are actually hanging a mass of 100 kg. Clear? So let's suppose we are hanging a mass of 100 kg from this face. Clear? So I can say from this face I am hanging here 100 kg mass. Clear? So we can say this is 100 kg. Clear? Okay. Now in this question it is also given shear modulus. So shear modulus is represented by G. This is 25 gigapascal. Or you can also represent it by neta. This one. Clear? Now what is my objective? My objective in this question is to calculate vertical deflection of this face. It means, now you can say here, whatever force that will act on this face, that is the tangential force, and we know due to tangential force shear stresses are generated. Clear? So directly I can write here, if I want to calculate deformation is given by shear force per unit area divided by, I can say because this is delta x, or directly we can write here formula, that is FL over A neta. Yes or no? Yes. So we can write like this, FL over A neta. Clear? So actually we defined here shear modulus. Shear modulus is given by FL over A delta x. Clear? So now we can say what is delta x. Let's suppose after some time let's suppose this face is, it will move like this. Clear? And we can see this should be like this. Clear? And we can say here this part we have delta x. Clear? So now we can actually calculate value of delta x. Value of delta x, this is given by FL over A neta. Okay, force is given to you 100 multiply G. Clear? And value of L it is given, that is 10 centimeter. So 10 into 10 to the power minus 2 divided by, if we are talking about area, so we can say area 10 into 10 into 10 to the power minus 4 meters square. And if I am talking about modulus of shear modulus, or we can say modulus of rigidity, then we can say this is 25 into 10 to the power, because this is giga. Clear? We have mega. Clear? 10 to the power 6. Then we can say deca, hecto, kilo, mega, giga. Clear? So we can say this is 10 to the power 9. Clear? So we can say delta x, this one is given by, I can say 1000 multiply 10 to the power minus 1 divided by, we can say 100 into 10 to the power minus 4 into 25 into 10 to the power 9. Now we can easily solve it. Clear? This is 100. Clear? 100 and 100, this one is cancelled out. Now we can say this is 25 and this is 10 to the power 5. Clear? So we can say 100 divided by 25 and multiply 10 to the power minus 7. Clear? Now we can write like this, this is equal to 4. Clear? So deformation on the face on which we are attaching a mass, this is given by 4 into 10 to the power minus 7 meter. Clear to everyone? So this is a value for deformation. Clear? So this is all about this question. We are going to now discuss question number 9.7, and in this question it is given to you 4 identical hollow cylindrical column of mild steel. It is already given mild steel support a big structure of mass 50,000 kilogram. So let's suppose I am saying here we have a structure like this. Let's suppose we have structure like this one. Clear? And mass of this structure is given to you 50,000 kilogram. Clear? Mass of this structure, this is given to you 50,000 kilogram. Clear? So we can say this is 50,000 kilogram. So capital M, we have 50,000 kilogram. Clear to you? Yes. So 4 identical hollow cylindrical column of mild steel, it is given 50,000 kilogram. Clear? The inner and outer radius of each column, actually support a big structure 4. Clear? So we can say here, let's suppose we have 4 column. Let's suppose this is 1, this one is 2. Clear? On the back side we have number 3. Clear? And let's suppose here we have number 4. Clear? So let's suppose we have a 4 column, and on this 4 column we are attaching this mass 50,000 kilogram. Okay, fine. Inner and outer radius of each column is given to you. It means we can say R in inner, means we can say inner radius. Inner radius we have 30 centimeter, and if I am talking about outer radius, this is given by 60 centimeter. Clear? Now, if we are assuming load that is distributed is to be uniform, then calculate compressive strain. Clear? So now first of all, let us try to understand total force that is exerted by this body. I can see total force, we can say this is 50,000 G. Clear? Now we can say this load is actually uniformly distributed in each column. So I can say compressive force acting on each column. Clear? So force acting on each column, this is given by 50,000 multiply G divided by 4. Clear? So now we can say, we can write like this 12500 G. Yes or no? Clear? We can say this is 12500 G. This is a force that is exerted on each column. Clear? Now if I am talking about area, we can say pi R naught square minus Ri square. Clear? So we can say this one we have pi by 7. Okay, outer radius we have 60. So we can say 60 square minus 30 square, and because this is in centimeter, so I can write here this is 10 to the power minus 4. Clear? So we can say this is equal to 22 by 7. We can apply here a square minus b square, a minus b, a plus b. So a minus b we have 30, a plus b we have 90, and this one is 10 to the power minus 4. Clear? So now we can say we know now area, this area in a meter square. Force exerted, or we can say compressive force exerted on each column, this is also given to you. Now what is my objective? First I will calculate here stress, and after stress, if I divide with Young's modulus, then definitely I will get here compressive strain. Clear? So how can I calculate here stress? Stress is given by, I can say, force acting divided by this area. Clear? So 12500 multiplied with G, that is 10. Clear? And area we know 22 by 7 into 30 into 90 into 10 to the power minus 4. Clear to you? Now first we calculate here value of stress, then we divide with Young's modulus. Clear? Yes. Now listen. If we talk about stress, this is given by, directly we can solve 10000 cancelled out. Clear? Here we have 10 to the power 5. So I can say 125 into 10 to the power 5 divided by 22 by 7 multiply. We can say this is 27. Yes. So I am writing just 3 into 9. Clear? So this is value of stress. Now if we want to calculate compressive strain is given by stress divided by, I can say, Young's modulus. Clear? So value of stress, this is given by 125 into 10 to the power 5 divided by 22 by 7 into 3 into 9. Clear? And it is divided by Young's modulus. Okay, value of Young's modulus. So value of Young's modulus, this is given by, for steel. Actually, whenever you will face such type of question, value of Young's modulus will always be given to you. Clear? So but at least for Young's modulus of steel you should know. Clear? So I am saying here value of Young's modulus, this is given by 2 into 10 to the power 11 Newton per meter square. Clear? So this is value of Young's modulus of a steel. Clear? So clear? So if I solve it, definitely I can get my answer. So we can say this one is what? This is 10 to the power minus 7 here. Clear? So this is 125 into 10 to the power minus 7 divided by 22 by 7 into 3 into 9 into 2. Clear to you? Now listen carefully. just we have to solve. So we can say this is 18, we can say this is 54, clear, or 54, I can say 125 into 10 to the power minus 7 divided by 22 by 7 into 54. Now approximately we can say, if we cancel it, it is approximately 8 times, clear. So I can say this is approximately 8 times, clear. If you multiply 22 with 8, you can write like this, 125 into 10 to the power minus 7 divided by 22 multiply 8. So 22 multiply 8, we have 16, 176, clear. So now we can see 17, if we multiply 17 with 7, we have 119, clear. So 119, it means this is we can say approximately we are getting 0.71, clear to you. So we can say this is a value of strain 0.71 into 10 to the power minus 7 in meter, clear. So this is a value of compressive strain that we are getting, clear. So this is all about this question. Now student, we are going to solve question number 9.8, and in this question it is given to you a piece of copper having a rectangular cross section of 15.2 mm and 19.1 mm is pulled in a tension with this force and producing only elastic deformation. Calculate resulting strain, clear. So now we know strain this is given by stress divided by Young's modulus, clear. So strain this is given by stress divided by Young's modulus, clear. So how can we calculate here stress, clear. Stress is given by force per unit area, force is given to you 44500, clear, divided by area. Area is given 15.2 into 19.1, and I can say this is mm square. So if I multiply it with 10 to the power minus 6, I can say this is converted into meter square, clear. Okay. Now if I am dividing with Young's modulus, clear. So if I am dividing with Young's modulus, because the material is given to you copper, so for copper we have Young's modulus value 1.2 into 10 to the power 11 Newton per meter square. Now you can say, sir, we have to memorize these values. No, not at all, clear. Whenever this type of question is given to you, definitely this value will also given to you, clear. So now you can say, sir, why in NCERT this is not given to us? Because in NCERT already in a chapter it is given in a table, clear. So actually publisher, or we can say in NCERT it is generally assumed that if you need any value you can reference that table, clear. So we can say I am taking this value from that table only. So this is 1.2 into 10 to the power 11, clear. So I can write like this, this is 1.2 into 10 to the power 11, clear. So if you solve it, definitely you will find strain that is produced in this copper wire having rectangular cross section area, clear. So now we can write like this 00, clear, into 10 to the power minus we can say this is minus 6 and this one is 11. So this is 10 to the power 5, I am saying this is 10 to the power minus 5, clear, and it is divided by 15.2 into 19.1, clear, and 1.2, clear. Now you can say, sir, we have a lot this type of calculation. Yes beta, we have, clear. So just take a simplification and definitely you will get an approximate result, clear. From here we can say this is 445 into 10 to the power minus 3, I am saying, clear, and let's suppose I am writing here this is 15, clear, I am saying this is 20, and let's suppose I am taking it 1, approximate result I am taking, clear. So if I divide with 15, I can say, or 5, I can say this is 3, we can say this is 89, clear. So now we can say approximately this is 4.5, clear, and we can say this is 1.5, clear. So approximately, I am not saying this is an exact answer, but approximately we are getting strain 1.5 into 10 to the power minus 3 meter, clear. So we can say this is a value of strain that is produced in this copper having rectangular cross section of area, clear. So this is all about this question. Now student, we are going to discuss next question, question number 9.9, and in this question it is given to you a steel cable with a radius of 1.5 centimeter supports a chair lift at a sky area. Okay, fine. If the maximum stress is not exceeding 10 to the power 8 Newton per meter square, what is maximum load the cable can support, clear. So now let us try to understand radius is given to you 1.5 centimeter. I can say this is 1.5 into 10 to the power minus 2 meter. Clear? Now it is also given maximum stress. So we can say maximum stress is given by 10 to the power 8 Newton per meter square. Clear? Sigma maximum 10 to the power 8 Newton per meter square. What is maximum load the cable can support? Clear? So if I am saying here stress, or we can say if I am talking about maximum stress, clear? So maximum stress is given by, I can say maximum load divided by area. Clear? So now we can say this is 10 to the power 8 equal to maximum load. Clear? Maximum load means we can say this is my objective, so I can say maximum load I will calculate. And what about total area? Because it is given having radius this one, so we can write area pi r square. This is cross sectional area. Clear? So I can say pi r means 1.5 into 10 to the power minus 2 whole square. Clear? From here we can calculate maximum load. So I can write like this, F maximum, this is given by 10 to the power, or we can say first pi 22 by 7 into 3 by 2 into 3 by 2 into 10 to the power minus 4 multiply. I can say maximum stress is given by 10 to the power 8. Clear? So now we can say this one we have 11. So 11 multiply 9 divide by 7 into 10 to the power 4. Clear? So we can say this is value of maximum force. Clear? So I can say 99 by 7 into 10 to the power 4 Newton. Clear? So now if you calculate, you can give me answer. This is 1, we have 2 left, so that is 4, we have 1 left, and this is 14.1 into 10 to the power 4 Newton. So we can say this is a maximum force that can be bear, or the maximum force that can be supported by this cable. Clear? So this is all about this question. Now student, we are going to discuss question number 9.10, and in this question it is given to you a rigid bar of mass 15 kg is supported symmetrically by 3 wires 2 meter long. Clear? So let's suppose I am saying this is a let's suppose this is fixed end. Clear? Here we have 3 wires and 2 wires is at the end. 2 wires are at the end like this. Clear? And we can say we have 1 wire at the middle. Clear? And they are actually supporting a rigid bar of mass 15 kg. So we can say, let's suppose they are supporting a rigid bar of mass 15 kg. Clear to everyone? Done. So a rigid bar of mass 15 kg is supported symmetrically by 3 wires, each having 2 meter long. So I can say we have 2 meter long wire. Clear? Now clear. Those at each end are of copper and middle one of iron. So we can say this is made up of copper, this one is also for copper, and this is for iron. Clear? Now we have to determine ratio of their diameter if each of having same tension. So we can say tension value is same in each wire. Clear? So now my question is here, how can we calculate here ratio of diameter? So first let us try to understand. If we are talking about delta L, this is given by FL over AY. Clear? Now we can say here forces, this is acting here, this is equal to tension, so TL over AY. Clear? Now in this question it is given value of L is same for all the 3 wires, tension is also same. If we are talking about Young's modulus is different. Clear? But it is also actually we are saying because this is in an equilibrium, so we can say deformation is also same in each wire. Clear? So can I write like this? A, this is equal to TL over, and we can say Y delta L. Clear? So now I think it is clear to you. T is same for each wire, L is same, delta L is also same. Clear? So from here I can say area, this is inversely proportional to Young's modulus. Clear to everyone? So we can say area, this is inversely proportional to Young's modulus. Clear? So now I can say here Young's modulus for iron. Clear? So we can say it is having determined the ratio of their diameter. Okay, so we can say we can write like this. Our objective in this question is to calculate diameter ratio. Clear? So now we can say this area, this area we can say this is equal to what? Pi d square by 4. It is directly proportional to 1 upon y. Clear? So we can write like this, d square directly proportional to 1 upon y. Clear? So now we can say, we can write like this, d is inversely proportional to 1 upon under root of y. Clear? So now I can write like this, diameter for copper wire, and we can say diameter for iron, this is equal to under root of y for iron, and this is y for copper wire. Clear to you? So now if I find here ratio of their diameter, if I find ratio of their diameter, we can see if you know the value of Young's modulus, directly you can calculate this ratio, the ratio of diameters. Clear? So now I am going to tell you what is value of Young's modulus for iron. Clear? And value of Young's modulus for copper. Clear? Yes. Now listen carefully. So first, if I am talking about Young's modulus for iron, Young's modulus for iron, this is given by, I am telling you value, this is given in a table in your book, 1.9 into 10 to the power 11, this is Newton per meter square. And if I am telling you Young's modulus for copper wire, recently I tell you this is 1.1 or 1.2, so we can say 1.1 into 10 to the power 11 Newton per meter square. Clear? So if we want to calculate diameter of copper wire, if we want to calculate ratio of diameter of copper and iron, we can write like this, under root of gamma Fe 1.9 into 10 to the power 11 divided by 1.1 into 10 to the power 11. We can say this one cancelled out. Clear? And if you calculate it first, you will find here some value, then if you take square root, you can get here this value is approximately equal to 1.3. Clear? So we can say like this, you will find here this ratio, diameter of a copper or diameter of a iron. Clear? So directly you can say definitely diameter of this copper wire that is situated at the end, that is having 1.3 times of diameter of iron. Clear? So this is all about this question. Clear? Now student, we are going to solve question number 9.11, and in this question it is given to you a 14.5 kilogram mass fastened to the end of a steel wire of an unstressed length 1 meter. Clear? So let's suppose I am drawing here one diagram. Let's suppose I am saying here we have a 14.5 kg mass. So let's suppose I am saying this is 14.5 kilogram. Clear? Okay. It is fastened to the end of a steel wire, okay, having length L, this is equal to 1 meter. Clear? So length of this steel wire is also given. Clear? It is actually having motion in a vertical circle. Fine. Angular velocity, it is also given, but in a revolution per second. Clear? So can we calculate here omega? Yes. This is equal to 2 pi f, or we can say 2 pi. We can say this is 2. So I can write like this, this is 4 pi radian per second. Clear to you? And at that time it is a bottom of a circle. It means at the lowest position. Clear? So at the lowest position, if we analyze here, what are the different forces this is acting? I can say here, number one force, this is acting mg. Clear? Definitely at lower position it is having certain velocity. So we can say tension force is also acting. Now if I am talking about non-inertial frame, at that time I can say a centrifugal force, this will act away from a center along a radius. So this is also given by mv square by r. Clear? So from here we can say value of tension T, this is given by mg plus mv square by r. Clear? So instead of r you can write here this is L. Clear to you? This is L. Clear? So we can also write like this, this one is equal to mg plus m omega square L. Clear? Now from here we can take common value m. Clear? This is g plus omega square L. Clear? We can write like this. Yes. Clear? So value of m, m means we can say mass, mass is given to you 14.5 mass. Clear? Value of small g, value of small g, this is given to you 10 plus I can say omega square L, omega is given, this is 4 pi. Clear? So 4 pi into 4 pi and multiplied with L. L is given to you 1 meter. So I can write here this is 1. Clear? So from here can we find here value of tension? Yes, this is 14.5. I can say this is 4 plus 16 pi square. Pi square is having approximately value 10. So I can say this is 160 and this is 170. So 14.5 into 170. Clear? From here you can write like this. This is 145 multiply 17 and this is in a Newton. Clear to everyone? Now, but what is my objective in this question? My objective is very clear. We have to calculate elongation of a wire when mass is at lowest position. Clear? So now listen carefully. So if I am talking about elongation, elongation means I can write like this: delta x, this is given by FL over AY. Clear? Here force, this is acting on this wire, that is tension force. So I can say this is tension T L over AY. Clear? Now we can put here all the values. So value of tension we know 145 into 17. Clear? Value of length we have, that is L. Clear? If we are talking about cross section area, this is given 0.065. So 0.065 into 10 to the power minus 4 multiplied with, now this wire is of steel. So what is value of Young's modulus? I think till now you have memorized this value, 2 into 10 to the power 11. Clear? So now we have to solve this expression and we can easily get value that is deformation or elongation of a wire when it is at its lowest position. Clear? So now concentrate. Yes. Now we can solve like this. Delta x, value of delta x, this one is given by, I can say 145 into 17, 145 into 17 divided by 0.065 into 10 to the power we can say 7 into 2. Clear? Now if you solve it, you will find here value of delta x. I am directly telling you here value because this is slightly calculative. Clear? So here you will get value 1.87 into 10 to the power minus 3. Clear? You will get here 1.87 into 10 to the power minus 3 meter. Clear? So you can solve this question like this. Clear? So actually this is a good question, and this type of question it may be asked in competitive examination like JEE or NEET, because in this question we have two concepts. First of all, you should know how to write, how to calculate tension value, because here we are utilizing a concept of motion in a vertical circle, as well as here we are also defining, we are also utilizing this delta x. This is equal to FL over AY. Clear? So now we can solve this question like this. Clear to everyone? Now dear student, we are going to discuss question number 9.12, and in this question it is given to you, compute the bulk modulus of water from following data. Clear? Initial volume is given to you 100 liter. Clear? So concentrate here. It is given in a question initial volume. So I can say initial volume is given, this is equal to 100 liter. Clear? 100 liter. Or and pressure increase, or we can say change in pressure is given to you 100 atm. Clear? ATM means what? Not automatic teller machine. Clear? ATM means atmospheric pressure. Clear? And value of 1 atm, it is also given to you 100 into 1.013 into 10 to the power 5 Pascal. This is given to you. Clear? And now final volume, this is given to you 100.5 liter. Clear? So final volume is also given to you. Clear? Now we have to compare bulk modulus of water, that of air. Clear? So first we calculate here bulk modulus of water. Clear? So how can we define bulk modulus? Bulk modulus is actually defined as a change in pressure over fractional change in volume. Clear? So change in pressure, this is given to you 100 into 1.013 into 10 to the power 5 divided by, I can say fractional change in volume. So what is change in volume? We can say this is 0.5 liter. I can say this is 10 to the power minus 3. clear. And we can say initial volume it is given to you 100 liter. So we can say we can multiply it with 10 to the power minus 3, clear. So we can say this one and this one cancel out, clear. And if you remove this decimal, I can say this is 10, clear. So now if you calculate, you can write like this, 1.013 divided by 5, clear, multiplied with 100 into 100, or you can say 1000, clear. That is nothing else, clear. So from here we can say this is 10 to the power 5, yes or no, yes or no, clear. So we can say this is equal to what? Yes, is there any missing? It is given 100 ATM, so this is value of ATM. It is also given 100 liter, so we can say that is 100 into 10 to the power minus 3, and here we have 0.5. Okay, done, everything is okay. So now from here we can say, we can write like this, yes, we have here 10 to the power 5 also, clear to you. 1.013 divided by 5, 100 into 1000 into 10 to the power 5. Now we can say if we multiply it with 10, then we can write like this, bulk modulus, clear. Sometimes bulk modulus is represented by K, and in NCERT it is represented by letter, that is capital B, clear. So bulk modulus is also represented like this. So I can say bulk modulus of water, it is also represented by beta, clear. So now we can say this is equal to 10.13 divided by 5, clear. And now I can say here we have 10, this is 1000, so 10 to the power 4, and we can say this is 10 to the power 9, clear. From here I can say 2.0, I can say 3, so 2.03 into 10 to the power 9 Newton per meter square, clear. So this is a value of bulk modulus of water, clear to you. Now actually we know bulk modulus of air, this is given by 1 into 10 to the power 5 Newton per meter square, clear. Bulk modulus of water is given, bulk modulus of air, this is given by 1 into 10 to the power 5 Newton per meter square. So now if I calculate bulk modulus of water divided by, I can say bulk modulus of air, this is given by 2.03 multiply 10 to the power 4, and this is Newton per meter square, clear to everyone, clear. So now we can say if we find here value of bulk modulus of water, so bulk modulus of water is 2.03 into 10 to the power 4 times of bulk modulus of air. Now why this value is coming so large? Because we can see the compressibility. If we talk about compressibility of air is very large compared to compressibility of water, clear. So that's why we can see that bulk modulus is defined as 1 upon compressibility. So compressibility of air is more, it means we can say value of bulk modulus of water we will find more, clear. So this is all about this question, clear. Now dear student, we are going to discuss question number 9.13, and in this question it is given to you, what is the density of water at a depth where pressure is 80 atm, given that its density at the surface is 1.03 into 10 to the power 3 kilogram per meter cube, clear. So now concentrate. Yes, in this question our objective here is to calculate density of water at a depth where pressure is 80 atm, clear. So can we find, let's suppose this is, we can say, let's suppose this is surface of a water, clear, and let's suppose we are talking about at this point, clear. It means we can say at this point pressure, let's suppose this is P1, it is given to you 80 atm, clear, and we know here we are having we can say that is 1 atmosphere, clear, yes or no, because this is a surface of a water, and definitely pressure, atmosphere is exerting a particular pressure on this surface, clear. So what is density of a water at a depth, clear. So density we have to find, pressure is given. So can we calculate first here change in pressure? Change in pressure we can say 80 minus 1, and we can say this is atm, clear. From here you can say this is 79 atm, clear to you. So now we can write like this, delta P, this is given by 79 multiply 1.013 into 10 to the power 5 Newton per meter square, this is given to you, clear. So delta P value is this one, okay, fine. Now it is also given, yes, Now can we calculate here change in fractional change in volume? Delta V by V? Yes, we can write like this. This is V minus V dash over V. Initial volume minus final volume upon initial volume. Clear? We can also write like this. This is mass upon density rho. Mass upon density rho dash over mass upon density rho dash. Clear? So we can say this rho dash is a density at this point. Clear? At this point we have here this density, that is rho dash, and let's suppose here we have rho. Clear? So now from here we can write like this. This is 1 minus this is actually rho. Clear? Yes. So here we have a rho. So we can write like this. This is rho by rho dash. Clear? Now actually we know, if we are talking about compressibility of water, compressibility of water. Now compressibility of water, it is represented by K. Clear? And this value is given to you. Here we have a particular value of compressibility. This is 45.8 into 10 to the power minus 11. Clear? This is a value of compressibility. Clear? Or we can say its unit is Pascal inverse. Clear? So now actually we also know bulk modulus. Clear? So bulk modulus, this is given by change in pressure over fractional change in volume. Clear? So from here we can also calculate fractional change in volume like this. This is change in pressure divided by bulk modulus. Clear? So fractional change in volume, we can say this is given by change in pressure. Change in pressure means this value we have 79 into 1.013 into 10 to the power 5 and divided by beta. Clear? Now we know 1 by beta. 1 by beta, this is equal to compressibility. Clear? So now we can multiply it with 79 into 1.013 into 10 to the power 5 multiplied with, we can say 45.8 into 10 to the power minus 11. Clear? So from here you can see fractional change in volume. Clear? So fractional change in volume, this value is given by 3.66 into 10 to the power. 3.66 into 10 to the power, we can say 3. Clear to you? 3.66 into 10 to the power 3. Clear? And this is a value for fractional change in volume, and this is a value. Clear? Now we can actually see this fractional change in volume, this is equal to 1 minus rho by rho dash. Yes or no? Yes. So from here we can see, now from here we can see, yes, from here we can say, we can write like this, 1 minus rho dash by rho, this is equal to 3.66 into 10 to the power minus 3. Clear? So from here you can write like this, rho dash by rho, this is equal to 1 minus 0.00366. Clear? So now it is also given density at a surface, we have 1.03 into 10 to the power 3. Clear? So now we can write like this. Yes. So from here we can see, we can write like this, rho dash, this is equal to rho 1 minus 0.00366. Clear? Now value of rho at a surface, this is given to you 1.03 into 10 to the power 3. Clear? And we can say this is 1 minus 0.00366. Clear? So if you calculate directly, we can say approximately I am taking it 1. Clear? Approximately I am taking it 1. Why? Because this value is very small compared to this one. Clear? So from here we can say that we are getting this value. This is density kilogram per meter cube. Clear to everyone? Clear? And if you actually calculate, you will find here 1.0, this is 1.034. Clear? 1.034 into 10 to the power, and we can say this is 3. So approximately we can say we are getting same value. Clear to everyone? So now, so we can say approximately there is a very less change in a density that we will find at a depth compared to the surface of water. Clear? So this is all about this question. Clear to everyone? Now dear student, we are going to discuss question number 9.14, and in this question it is given to you, compute the fractional change in volume of a glass slab when subjected to a hydraulic pressure of 10 atm. Clear? So concentrate. Clear? Now we have to calculate fractional change in volume. Fractional change in volume means we have to find delta V by V, and this is question mark. Clear? Now because this is glass slab, so for glass slab bulk modulus value we have, this is given to you 37 into 10 to the power 9 Newton per meter square. Now you can say, sir, from where you are getting this bulk modulus value? Actually always there is a standard table for a given material, that what will be bulk modulus value, what is the modulus of elasticity, we can say Young's modulus, shear modulus, every value is fixed. Clear to you? Yes. So now we can say, we are assuming here in this question bulk modulus is given 37 into 10 to the power 9 Newton per meter square. Clear? Now can we calculate here fractional change in volume when it is subjected to a hydraulic pressure? So hydraulic pressure means what? Let us try to understand. Clear? Let's suppose we can say here we have an object. Let's suppose this is cube. Clear? And from for this cube, pressure is exerting from all the sides. Pressure is exerting from all the sides. So we can say this one. Clear? So we can say this is a cube and pressure is exerted from all the sides. Clear? So we can say this change in pressure, that is known as hydraulic pressure here. Clear? So I can say change in pressure, this is given to you 10 atm. Clear? 10 atm means I can say 1.0132 into 10 to the power 5. Clear to you? So now we can say, if I write here 10.132 into 10 to the power 5 Newton per meter square, or you can say this is Pascal. Clear? So now what is our objective? Fractional change in volume. So I can say bulk modulus, or bulk modulus is also indicated by beta. Clear? So bulk modulus, this is given by fractional change in pressure over fractional change in volume. Clear? So I can write like this: fractional change in volume, this is given by delta P divided by beta. Clear? So now what is change in pressure? We have 10.132 into 10 to the power 5 divided by, now beta. Beta means we can say that is bulk modulus. Bulk modulus value is given 37, or actually you can say this is beta. Clear? No problem. This is beta. So we can write like this: 37 into 10 to the power 9. Clear? So now if you solve it, we can write like this: 101.32 into 10 to the power 4 divided by 37 into 10 to the power 9. Clear? So if you solve it, clear? So if you solve it, you will find here value approximately, you can say, if you multiply it with 3, it will be more than yes, it will multiply it with 3, definitely it will be more than 100. Clear? So it means definitely you will get here value 2 point something. Clear? So correct answer you will get 2.74 into 10 to the power minus 5. Clear? And this is a value for what? This is bulk modulus, this is fractional change in volume. Clear? So definitely you will not find any unit. Clear? So this is all about this question. Clear to everyone? Now dear student, we are going to discuss question number 9.15, and in this question it is given to you: determine the volume contraction of a solid copper cube 10 cm on an edge when subjected to a hydraulic pressure of 7 into 10 to the power 6 Pascal. Clear? So now concentrate. Actually our objective in this question is to calculate change in volume. Clear? Now for a copper bulk modulus value we have 140 into 10 to the power 9 Newton per meter square. Clear to everyone? So this is value of bulk modulus for copper cube. Clear? Now our objective, okay, one more thing is given to you: hydraulic pressure. Hydraulic pressure means we can say change in pressure. This value we have 7 into 10 to the power 6 Newton per meter square. Clear to you? So now we have to find change in volume. Clear? So how can we calculate? We know bulk modulus, or yes, generally students have a practice to write bulk modulus by beta, so I am also writing with beta. So bulk modulus beta, this is given by change in pressure over fractional change in volume. Clear? So I can write here fractional change in volume, this is given by change in pressure divided by beta. Clear? So I can write like this: change in volume, this is given by change in pressure divided by beta and multiplied with volume V. Clear? So now I can say change in volume. Clear? This is given by delta P by beta into V. Clear? So change in pressure we have 7 into 10 to the power 6. Clear? Divided by beta. Beta means we can say this is 140 into 10 to the power 9. Clear? And volume V. So what is initial volume? Initial volume, actually it is given, we have a copper cube. Cube means we can say this is 10 into 10 into 10, and we can say this is 10 to the power minus 6 meter cube. Clear? Because this is given in a centimeter, we can convert into meter cube. Clear? So now we can say, we can write like this. This is 20. Clear? So 10 to the power minus 3 divide by 20 into, I can say this is also 10 to the power minus 3. Clear? So from here we can write like this, 100 by 20. Clear? 10 to the power minus 8. Clear? So from here we can say change in volume we are getting 5 into 10 to the power minus 8 meter cube. Clear? So this is the answer of this question. Clear to you? Now dear student, we are going to discuss question number 9.16, and in this question it is given to you, how much should the pressure on a liter of water be changed to compresses it by 0.10%. Clear? So it means it is given to you, fractional change in volume we have 0.10 divided by 100. Clear to you? And actually we know bulk modulus of water, this is given by 2.2 into 10 to the power 9 Newton per meter square. Clear? 2.2 into 10 to the power 9 Newton per meter square. This is value of bulk modulus. Clear? Now what is our objective? Our objective here in this question is to calculate how much should the pressure on a liter of water. Clear? It means I can write like this, bulk modulus, this is given by change in pressure over fractional change in volume. Clear? So now we can write like this, delta P. Delta P, this is given by beta delta V by V. Clear? So bulk modulus value we have 2.2 into 10 to the power 9 multiply fractional change in volume. Fractional change in volume given to you 0.10 divided by, I can say this is 100. Clear? So if we remove this decimal, definitely I can say this is 100. Clear? So we can say this is 10 to the power 5. Clear? And we can write like this, this is 22 into 10 to the power 6. Clear? So we can say this is value we have Newton per meter square, or you can say this is Pascal. Clear? So this is all about this question. Clear? Now student, we are going to discuss next question, question number 9.17, and in this question it is given to you, anvils made of a single crystal. Anvils made of a single crystal of diamond with the shape as shown in a figure are used to investigate behavior of materials under very high pressure. Okay, fine. Flat faces at narrow ends of anvil has a diameter of 0.50 mm. Okay, fine. And the wide end are subjected to a compressional force of 50,000 Newton. Okay, fine. What is pressure at the tip of anvil? Clear? So actually we have a very simple question, just the language of this question is confusing. Clear? Simple question is given to you. Let's suppose we are exerting here a force that is 50,000 Newton. Clear? At this point we have diameter. So whatever flat face we have, diameter is given to you D. This is 0.50 mm. This one is given to you. Clear to you? So now can we find here radius? Yes. Value of radius, this is given by 0.25 mm. Clear? Now what is my objective? My objective in this question is to find value of pressure at the tip of anvil. Clear? So I can write like this, pressure is given by force per unit area. Okay, so force value we can say this is 50,000 divided by area. So I can say this area is given by pi, or we can say that is 1 by 4 into 10 to the power minus 3 whole square. Clear? We can write like this. So from here you can say this is 16 into 50,000. Clear? Divided by pi into 10 to the power minus 6. Clear? So now I can say we can write like this, 16 multiply 5. 16 multiply 5, we can say this is 80. Clear? We can say 10 to the power 4 divided by pi into 10 to the power minus 6. Clear? 16 into 10 to the power 5. 16 into 10 to the power 5. So we can say 16 into 5, 80, 10 to the power 4 divide by pi into 10 to the power minus 6. Clear? So I can say 80 divided by pi into 10 to the power 10. Clear? So we are getting this much of pressure. So pressure we can say 80 divided by 3.14 into 10 to the power 10. Clear? So from here we can say, let's suppose we are assuming this is 81. At the time we can say 27. So approximately we are saying 27 into 10 to the power 10 Pascal. Clear? So we can say this is a value of pressure that is exerted at the tip of anvil. Clear? So this is all about this question. Now student, we are going to solve question number 9.18, and in this question it is given to you a rod of length 1.05 meter having negligible mass is supported at its end by two wires of steel. Two wires of steel. Number A wire is a steel wire and second wire is made up of aluminium. Okay, fine. It is also given both are having equal length. Okay, and cross sectional area of wire A and wire B is different. For A, cross sectional area is given to you 1 mm square, and for B, cross sectional area is given to you 2 mm square. Okay, fine. So at what point along rod should a mass small m be suspended so that in order to produce number one condition equal stress, and number second condition we have equal strain in both steel and aluminium wire. Clear? So now concentrate here. First I am going to solve here condition number A. Listen carefully. Let's suppose I am saying here tension that is going here, this is T1 and this one is T2. Clear? And we know if this is a weight, I am saying here this is weight, let's suppose this weight is W. Clear? And let's suppose we place this weight at a distance x from this side. Clear? I am assuming here, let's suppose initial we have total length that is small l. So from this we can say wire number B, the position of this weight we are assuming this is L minus x distance. Clear? So now how can we write? In a first condition it is given to you equal stresses is generated in both wire. So can we write like this? T1 upon A1, this should be equal to T2 upon A2. Clear to you? Now we can also write like this, T1 upon A1. So A1 means we can say this area. So I can say yes, this is 1 mm square. Clear? I can say this is T2 by 2. Clear? So from here we can write like this, T2, this is equal to twice of T1. Clear? We can say T2, this should be equal to twice of T1. Clear? So this is equation number 1. Now what we can do, you can concentrate here. Actually this rod is having rotational as well as translational equilibrium. Why? Because you can say the net horizontal force and net vertical force both are 0. Clear? And we can say this rod is also not a rotating condition. Clear? It means let's suppose if I take here torque about this weight. Clear? So how can we write? If I am taking here torque about, let's suppose I am saying this point O. So torque about O. How can we write? We can say due to this T1 we have a clockwise rotation. So we can say T1 multiply X. Clear? Now if I talk about T2, so due to this T2 we are getting anti-clockwise rotation. Clear? So I can write this is T2 multiply L minus X, and I can say this is equal to 0. Clear? So from here we can say T1X, this should be equal to T2 L minus X. Clear? Now in this question it is given T2, this should be equal to twice of T1. So T1X, this should be equal to twice of T1 L minus X. We can say T1 and T1 both are cancelled out. Clear? So value of X, this is given by twice L minus 2X. Clear? So from here we can say value of X, this is given by 2L by 3. Clear? This value is given by 2L by 3. So now we can say value of L. Value of L we can say we have 1.05. Clear? So if we multiply it with 2, we can say this is 2.10 divided by 3. I can say this is 0.70 meter. Clear? Value we are getting in a meter. Clear to everyone? This is in meter. Clear? So now we can say if we place this weight at a distance 0.70 meter from this steel wire, at the time we will get equal stresses in both wires. Clear to everyone? So this is all about part number A. Clear? Now Now here we are going to solve part number B, and in part number B it is given to you equal strain in both steel and aluminum wire. Clear? It means we can say delta L1 it should be equal to delta L2. Clear? Now we can also write like this. This is stress upon I can say this is stress upon Young's modulus. Clear? And this is also stress upon Young's modulus. Clear? Now here I am talking about Young's modulus of aluminum, and I am saying here this is Young's modulus of steel. Clear? So what is value of stress in wire number A? I can say this is given by T1 divided by, I can say area of this steel wire we have 1 mm square, and we can say this is given by 200 into 10 to the power 9. Clear? And this should be equal to, now we can say, let's suppose T2. Here we have T1 tension in this wire, T2 tension in this wire. Clear? So I can say T2 divided by, now cross sectional area is given to you, this is 2, and multiplied with, I can say multiply with what is value of Young's modulus for aluminum wire. This is equal to 70 into 10 to the power 9. Clear? So now we can say this is a equal stress condition, equal strain condition. Clear? So we can say 10 to the power 9 and 10 to the power 9 both are cancelled out. 0 and 0, this one is also cancelled out. Clear? So now we can say T1 divided by, I can say this is 20, this should be equal to, clear? T1 divided by 20, this should be equal to, I can say T2 divided by, I can say this one is 40. Clear? I can say this one is 40. Clear to everyone? 10 to the power 9 is cancelled, 0 and 0 cancel. Fine. So here we are getting one relation T1, this should be equal to 10 by 7 times of T2. T1, this should be equal to 10 by 7 times of T2. Clear to everyone? So this is equation number 1. Clear? Now let's suppose I am saying, let's suppose I am placing this weight at a distance x from this wire. Clear? So I can say, let's suppose this is x. So now we can say this value we have L minus x. Clear to everyone? So now from here, if I take here torque about this weight, clear, or let's suppose I am saying this is point O. So if I take here torque about this point O, then how can we write? Directly we can write like this, T1x, this should be equal to T2 L minus x. Clear? Now we can put here value of T1. Clear? So T1 value we have 10 by 7 T2 multiply x, this should be equal to T2 L minus x. We can say T2 and T2, this one cancelled out. Clear? So if we solve it, we can say 10x, this should be equal to 7L minus 7x. Clear? So from here you can say, I am writing this side, where I will write this side. Clear? So 17x, this should be equal to, I can say 7L. So value of x, this is given by 7L by 17. Clear? 7 by 17 into value of L. Value of L we have 1.05. Clear? So if you multiply it, you can see here we are getting 7.35 divided by 17. Clear? So yes. Now listen. Yes. Now from here you can see, if I write here value of x, this is 7.35 divided by 17. Clear? So now if you divide it, you can say 7, 3, 51, 4, 68 and 585. So 7.4 something. Clear? So we can say we are getting here this value 0.4 and I can say 3. Yes, correct. Absolutely correct. Clear? So we are getting the value of x, this is equal to 0.43 meter from this steel wire. Clear? So it means if we place this weight at a distance of 0.43 meter from steel wire, at the time we will find equal strain in both wires. Clear? We will find equal strain in both wires. Clear? So this is all about this question. Clear to everyone? Now student, we are going to discuss question number 9.19, and in this question it is given to you a mild steel wire of 1 meter and cross sectional area 0.50 into 10 to the power minus 2 centimeter square is stretched well, okay, within its elastic limit horizontally between two pillars. Fine. A mass of 100 gram is suspended from midpoint of a wire. Fine. Calculate the depression at midpoint. So now fully concentrate on this screen. Clear? My dear student, this question is actually very good question, and most probably this type of question you will find when you will move to higher classes. Let's suppose if you adopt civil engineering, let's suppose if you adopt mechanical engineering, at that time you will find a particular strength of material subject. In this you will find this type of question, and there you will utilize differentiation or integration approaches. Clear? But can we solve this question here? Yes, we can solve it. Clear? So how can we solve this problem? So for that, one concentrate on a screen. Now listen carefully. In this question it is given to you, let's suppose we have a pillar. So let's suppose I am saying this is one pillar, let's suppose this is another pillar. Clear? Let's suppose we stretch a wire between these two pillars. Clear to you? And let's suppose I am assuming distance between these two pillars we have, that is 2L. Clear? Distance between these two pillars is given to you twice of L. Clear to everyone? Done. Now, yes. Now we can say, let's suppose if we place a weight at the midpoint of this wire, at the time what will happen? At that time actually this wire becomes like this. Yes or no? Clear? Clear? So let's suppose at the time I am saying, let's suppose here you can place, this is W. Clear? And we are having here a sagging. This is known as sagging. Clear? And I am saying this value we have X. Clear? And definitely you know this value we have L, and this one value we have L. Clear? Let's suppose I am saying this is theta, this one is also theta. Clear? Now let's suppose I am saying this is A point, this is B, and let's suppose this is O. Clear? So first, can we calculate here what is change in length we are getting? Yes. How can we calculate? So change in length, this is given by, I can say AO plus OB minus, we can say twice of L. Yes or no? So now what is value of AO? Listen carefully. Now actually we know, if we concentrate on ACO, clear? This is a right angle triangle. If you concentrate on ACO, this is right angle triangle. So right angle triangle, it means you can apply here Pythagoras theorem. So we can write like this, value of delta L, this is given by AO under root of L square plus X square. Clear? Same value you will getting for OB. Clear? Under root of L square plus X square minus. Clear? Minus. We can say this is equal to twice of L. Clear to everyone? So now from here we can say this is equal to twice of under root of L square plus X square minus 2L. Clear? Now what I am doing here, I am taking here 2, this is X square plus L square power half minus 2L. Clear? Now let's suppose I am saying this X is very less compared to, or actually you can also write like this. First I am taking this L square common. So this is L, I can say 1 plus X square upon L square, this is power half minus 2L. Clear? Now actually we can apply here, this is 1 plus x to the power n. Clear? So 1 plus x to the power n, it means we can write this is 1 plus nx. Clear? When, because this ratio x square upon L square is very less compared to value 1. Clear? So we can write like this, twice L, 1 plus, I can say this is 1 by 2 x square upon L square. Clear? And I am taking here, this is also in this bracket. Clear? So from here we can say 1 and 1, this one is cancelled out. Clear to everyone? Yes. Now from here we can see what is change in length we are getting. Change in length we are getting 2L, and we have here 2L square. So I can say this is x square divided by L. So my dear student, can we calculate here strain? Yes. Strain is also calculated by delta L by 2L. How can we, because we can say original length we have 2L and change in length we are getting delta L. So from here we can say x square divided by twice L square. Clear to everyone? So this is one of the results that we are getting. Strain, if we are talking about strain that is produced in this wire, this is equal to x square upon 2L square. Clear? Now concentrate on this screen. Yes. Now from here you can see, let's suppose if I am saying to you, let's suppose here we have tension T1 and let's suppose here we are having tension T2. Clear? Or actually you can say you are placing this at a midpoint. So definitely T1 and T2 it will be same. Clear? So I am saying here this is T1 and let's suppose this is this one. Both are having same. Clear? So I can say let's suppose tension T. Clear? Now we can say if I take here two components of a tension in an upward direction, both will be T cos theta. Clear? In this direction we will find this is T sin theta and this one is also T sin of theta. Clear? So from here you can write like this, 2T cos of theta, this should be equal to W. Clear? 2T cos theta, this should be equal to W. Now my objective in this question is to calculate cos theta. So if I consider here right angle triangle ACO, clear? From here I can say value of cos theta, this is given by x upon under root of x square plus L square. Clear to everyone? So now we can write here like this. Okay, first we calculate here value cos theta. So from here if I take here common, I can say this is 1 upon, if I am taking here L square. So how can we write, this is important. So okay, can we write like this, x upon L square plus x square power half, we can write like this. Clear? Now cos theta, this is equal to x upon, I am taking here L common. Clear? So L square common, so we can say here we have power half, so this becomes L. I can say this is 1 plus x square divided by L square power half. Clear? Now we can say this x is very less compared to 1. Clear? Now we can say this x is very less compared to 1. Clear? So can we write like this, we can say cos theta, this is equal to x by L. Clear? We are getting this one is very less compared to x, so I can say cos theta, this is equal to x by L. Clear to everyone? Yes. So now we can put this value in this equation, 2t cos theta equal to W. Now you can say, sir, what you are doing? Actually my objective in this question first to calculate tension. Clear? So now I am removing this one. Now from here we can see value of t, this is given by W upon 2 cos of theta. Clear? W upon 2, value of cos theta we have x by L. Clear? So from here you can write like this, t, this is given by WL upon twice x. Clear to you? Yes. Now if I find here, because my objective here is to calculate depression means value x. Clear? So can I say, can we calculate here value of stress? Yes. Stress we can say this is given by T by A, or we can say this is equal to WL over 2AX. Clear? Now can we calculate here Young's can we calculate here value of Young's modulus? Yes or no? Yes, we can calculate. Clear? Now listen carefully. So now if I write here, my objective is very clear, to find value of strain. Yes or no? So we can write like this, Young's modulus. Young's modulus is given by stress over strain. Clear? Value of stress we have. Stress value is given to you WL over 2AX, WL over 2AX, and it is divided by, I can say strain. Strain is given to you, this is x square divided by twice L square. So from here you can say y. This value is given to you W, we can say 2 and 2 cancel out, WL cube divided by, we can say AX cube. Clear? So from here can we calculate value of x? Yes, definitely. I can say value of x cube, this is given by WL cube divided by AY. Clear? Now I can write here value of x. Clear? So value of x, this is given by L, W upon AY, it power 1 by 3. Clear? So now I can put here value x. Clear? Value of x, this is given by L. L is given to you 1 meter, so I am writing here 1 W. So weight is given 100 gram mass we have, so we can say this is mg. Yes or no? So we can say this is 0.1 kg, or multiply with 10, I can say this is 1 divided by cross sectional area. Area is given to you 0.5, it means 1 by 2 into 10 to the power minus 2 centimeter square. I can convert into meter square like this. Clear? Now value of Young's modulus, this is steel wire. So for steel wire you can say we have 2 into 10 to the power 11. Clear? And we can say this is power 1 by 3. I can say this one and this one cancelled out. We have 10 to the power minus 6, this is 11. So 10 to the power 5, yes. So we can say 1 upon 10 to the power 5 and power 1 by 3. Clear? So actually you can also write like this, let's suppose if I say this is 1000, or okay, you can do it like this, 1 upon this one, clear. Now let's suppose if inside I multiplied with 10 and divide with 10, clear. If I multiplied with 10, this become 10 to the power 6 and it will come out to be 100. So this is 1 by 100 and I can say this is 10 to the power 1 by 3, clear. So now if you take here square root, clear, like square root of 8 we have 2, so 2 point something, clear. So we are getting here value of x that is near about we can say 2 point something something, clear. So if we exactly write here all the values, clear, so we will get here this is near about 2 centimeter, clear. So or actually we can say here this is 2 centimeter, approximately you will get 2 centimeter, clear to you. So like this we can calculate here sagging portion, or we can say the amount of this the amount by which this we can say mild steel wire, this sags this sag when we attach a particular weight on at the midpoint of this wire, clear to everyone. So this is all about this question. So important part in this question we have only that one, that how can we proceed. First we find here change in length, then we find here strain, after strain we find here definitely a relation between tension and weight, 2t cos theta equal to w. Then we find value of cos theta, then we find tension, after that we find stress, after that we find Young's modulus, clear, and after that we can calculate value of x, clear. So this is all about this question. Now student, we are going to discuss question number 9.20, and in this question it is given to you, we have 2 strips of metal are riveted together at their ends by 4 rivets, clear. So now try to understand this question. Let's suppose here I am having, this is a metallic strip, clear, and let's suppose here we also have one more metallic strip, clear. Let's suppose if I attach here 4 rivets, so let's suppose rivet number 1 we can say 2, clear, rivet number 3 I can say this one, and rivet number 4. So let's suppose here we have 2 metallic plates and these metallic plates are attached to each other like this, clear. Let's suppose I am exerting here external force F, let's suppose here I am exerting force F. So we can say, actually we can say here 2 forces are acting in a tangential direction, clear. So this tangential directional force, due to this tangential directional force it is given here, actually it is resisted by a diameter of a rivet that is 6 mm, fine. So what is maximum tension that can be exerted by the riveted strip, clear. Shearing stress value, maximum value of shearing stress is given. Now listen carefully. First if I calculate here total stress, I can say actually this is shear stress. Shear stress I can say force per unit area, clear. Now if I write here force on each rivet, force on each rivet, force on each rivet, clear, this is given by F by 4A, clear to everyone, because we have total 4 rivets and force on each rivet, this is given by F by 4A, clear. Now if we find here because here our objective here is to calculate maximum shear stress, clear. So now we can say, now we can say here, we can write like this, this F by 4A, this should be either equal or less than given maximum value of shear stress, this is 6.9 into 10 to the power 7 Pascal, clear. So my question in this, my objective in this question, we have shearing stresses on the rivet, clear. So my objective here is to calculate maximum tension, clear. What is maximum tension? It means we have to calculate here F maximum, clear. So we can say F maximum, this should be equal to 6.9 into 10 to the power 7, it is multiplied with 4 times of A. So this is 4 times A. A means we can say area. Area is given to you, just diameter is given 6 mm. So pi by 4 into 6 into 10 to the power minus 3 whole square, clear. So this is 6 into 10 to the power minus 3 whole square, clear. So if you calculate here, you can see, if you calculate here, we can write like this, F maximum, this is given by 6.9 into 10 to the power 7 into pi into, we can say this is 216 into 10 to the power minus 6, clear. So now if we calculate, clear, so we can write like this, value of maximum tension that is given by, or maximum tension value given by, approximately I am taking this is 7. So I am just calculating here approximation. Clear? Approximate calculation I am taking here. So now I can say this value we have 7 multiply. This one is what? 10 to the power 7. Clear? And I can say this is pi. I am taking approximately this is 3. Clear? And this is what? 216 into 10 to the power minus 6. Now we can say 10 to the power 7 we have. This one is cancelled out. We have only 10 left. Clear? So now we can say we have 21 into 10 into 216. Clear? If you multiply it with 21, you can write like this. We have 6. Clear? We have 12 left. We can say we have 33, we have 3. So 42 and 3, this is 45. Clear? And we can say multiplied with 10. Clear? So maximum tension we are getting in this question, that is equal to T. This should be equal to 45360 Newton, or you can write like this. This is 45.360 kilonewton. Clear? So this is all about this question. Clear? Now student, we are going to discuss question number 9.21, and in this question it is given to you, the Marina Trench is located in Pacific Ocean and at one place it is nearly equal 11 kilometer below surface of water. Okay, fine. The water pressure at the bottom of a trench is given to you 1.1 into 10 to the power 8. So we can say pressure at bottom, this is given 1.1 into 10 to the power 8 Pascal. Clear? Now if we talk about pressure at the surface of a water, we can say that is atmospheric pressure, and this is given by 1.0132 into 10 to the power 5. Clear? So if we find here change in pressure, we can say this atmospheric pressure is almost negligible compared to this one. Clear? So directly we can say it is approximately equal to 1.1 into 10 to the power 8 Pascal. Clear to everyone? Yes. Now it is also given a steel ball. Okay, steel ball is given to you. Do you know bulk modulus value? I am telling you bulk modulus value for this steel ball. This is given by 160 into 10 to the power 9. Clear? 160 into 10 to the power 9 Newton per meter square. Don't bother about this value. This value will be given to you in a question always. Clear? So beta is given to you 160 into 10 to the power 9 Newton per meter square. Fine. Now what is the other values are given to you? Initial volume. Initial volume is given 0.32 meter cube. Clear? Now my objective is what? My objective in this question is what is the change in volume of a ball when it reaches to bottom. Clear? So now we can see beta. Beta means we can see bulk modulus. This is given by change in pressure over change in volume over V. Clear? So can we write like this? Delta V by V. This is given by beta. We can say delta P by beta. Clear? So now we can say we can write like this: change in volume delta P by beta multiplied with V. Clear? So change in volume. Now what is value of change in pressure? Change in pressure I can say that is 1.1 into 10 to the power 8 multiply. If I talk about volume, so volume means initial volume, we can say 0.32 divided by, we can say here we have beta value we have 160 into 10 to the power 9. Clear? So now we can say approximate, let's suppose if I remove this decimal, I can say this is 5 times. Clear? Yes or no? So we can say this one and this one cancel out, we have only 10 left. So 11 divided by 50 into 1 by 1000. Clear? We can write like this. Clear? So from here you can say this value we are getting 11 by 5 into 10 to the power minus 4. Clear? So this value we are getting approximately 2.2 into exactly value we are getting. This is a change in volume. Change in volume we are getting 2.2 into 10 to the power minus 4. Clear? So this is all about this question, and we can say this is change in a volume of a ball when it reaches to bottom. Clear? So this is all about this question. So dear student, this is all about NCERT and exercise solutions of chapter number 9, mechanical properties of solids. Definitely you enjoyed this session, as well as here you will find some key concept as well as the exact solution of all the questions. Clear? So this is all about this session. Thank you so much.